Hello YouTube and welcome to my first Impl video where I've been converting MeatPack, which is a Python and a C library, into a Rust implementation. So MeatPack is a way of compressing G-code or packing G-code and effectively doubling the data rate when we're trying to send that over a serial connection to a 3D printer. So it was created and authored by Scott Mudge, who did a histographic analysis of G-code files. If I scan down here, part of the repo here, he found out that after looking at all the characters in a G-code file, which is typically made up of G's, X's, Y's, and numerical characters, that actually G-code is mostly represented by 15 characters. Up to 93% of a G-code file is just the 15 of the full ASCII range. So from that, he found out, well, why don't we, rather than represent G-code as a full U8 bit, could we not represent G-code as a U4, or the 50 most commonly found characters in G-code as U4s? We can then pack those together as a U8, effectively doubling the rate. And then if we have the 16th bit as a flag, that can then highlight, we are now getting to the stage where we want to, we've got an 8-bit full character that's not represented by those 15 most common. We can flag that using the 16th bit. So then the serial just reads, the interpreter would read across that and just read that U8 as a full U8. It also has a bit of a control layer. We're using special characters to highlight whether a specific, MeatPack is turned on and off in a G-code file, so we can have this bit of control over which bits of a G-code file have been packed or not packed using the algorithm. So yeah, I've kind of briefly discovered how it works, but here's a visual demonstration. So we take a G-code length here, G1 x 113. Normally, each of those characters is represented by a single U8 ASCII character, and that resolves to a total of 27 bytes. So if we take the 50 most commonly found, and if I quickly show you the lookup table, which we'll be referring to later, if we go to meatpack.py, so we've got this lookup table to say, given a value, what should the 4-bit representation be? So here for 0, 0, 1 for 1. So it's converting so 2 is actually going to be represented by 2, not the ASCII. If you look up the ASCII value, it's not 2. So this is the reverse, the lookup to say, that's the 4-bit representation. We can then use that to then pack 2 of those to a single U8. I'll go back to that. Back down to So what we're doing is then taking those two, giving them their 4-bit representations, combining those two together as a single U8, and then we've got effectively G1 as a single byte, and we do that so forth throughout the string, highlighting some cases where we do actually have a full width character, such as a Y. We'll use the special flag that we set the 16th bit to say, hi, the next byte following is a full width character, read it as a full width byte, and that's a way of packing that code. So those show us we get down from 27 bytes to 16 bytes by doing that. We can further compress it by just removing white space entirely, because in G-code white space bears no meaning or has no significance in the interpretation. It just ignores it during interpretation. So we can actually just strip that entirely out. We often just use white space for human readable G-code. So that actually then reduces it to 13 bytes, which is effectively a double compression. So it's half the size of what we got. So that's what we're going to be building out in a Rust library. So hopefully you'll be able to follow me on this journey. Like I say, the MeatPack algorithm's already out there, so hopefully this will help you understand how it was built, maybe help you use it in your own projects, but also for me it's a good way of just remembering how I did it when it comes to potentially maintaining it in the future. So to start off, I've got a blank cargo library, And the part of the meat of this MeatPack algorithm is all around the lookup tables. How are we going to convert our U8s to U4s, and then also then how do we do that packing, which is a bit of bit shift manipulation. And we want to do that all in a no-stud environment as well, because we want to probably unpack on an embedded device such as a 3D printer. So in this library, we're going to first of all, of course, declare that it's a no-stud library. So we're not going to have we're not going to have vectors available to us and anything with a lock. There we go, no stud. And we're gonna, so I've put all the components of the library into a separate folder or module called components. Because in the full library we have created a command line interface as well, which I don't think we'll get to in this this video, but we'll see how we go. So we've created the components module, and we'll create instantiate that, and then I also then created the first the module submodule within that, which is called meat, which is where the meat of the algorithm exists. We create meat.rs, and like I said, the first part of this algorithm is to create those lookup tables for our common characters. So we want a forward lookup and a reverse lookup. So I've just my reference up here, so I remember how I did it. So right, the first lookup. Let's do the reverse lookup then. So given a let's do the forward lookup. So yeah, given someone passing us a U8, let's see what the U4 representation might be. So we can do it. It's going to be a pub const. So the function is already going to be evaluated. So we can evaluate it at compile time. Because we already know what the values are, it's just effectively doing a check of, given a U8, what the U4 will be. So we can do forward lookup. And in this, we're going to receive a byte. So some kind of pointer to a byte. There is an additional bit with this algorithm where, given if you're factoring in no spaces or are including no spaces in the packing algorithm decides whether to use one of these U4 characters as representing a space or representing E. So we'll see that in. So we need to put a flag here called no spaces, whether to say that we are dealing with meat packing whilst considering spaces or not. And this is going to return an option. Whoops. And that's going to be a U8. But it's going to be a U8 with the least significant bit being the U4 that we're interested in. Okay, so there's no kind of U4 representation in Rust, so we're going to use the least significant bit as our U4 representation. Then we'll bit shift them around to merge two together. So this is then we're going to match that byte on whether it is, and these are the characters that we're interested in. So the first one is 0. It's going to be one of our 15 most commonly used characters, and if it is, then we're going to also return some 0. So it's going to be our first of the U4s. Noting that, of course, in ASCII 0 is not 0. Actually, can I quickly find out what it is? If I do this, byte. There we go. There we go. It's 30, so it's not actually 0 in the ASCII range. So we got that, and then we need to do one. Oops. We want to do. Yeah, of course, it's going to be. This is going to be the byte. So that's what I meant to do. Here we go. So it's got to be the byte that is equivalent to ASCII 0. The byte that's equivalent to ASCII 1. Then we're going to return sum 1. And let's copy this, and we're going to do all the way down to 9. So 2, 3, 4, 5, oops. 4, 5, 6, 2, 3, 4, 5, 6, 7, 8. 8. 9. So, as you'd expect, whoops, all the numerical characters here are represented in the U4s because they're the most commonly appearing in G-code, and then followed by the period. I'll give that one as 10, and then this is then followed by, and this is where the no spaces comes in. So if it is E, we may be interested in it if we're not considering no spaces. So if we go match on E, and if no spaces is true, we can then actually consider it as one of the U4s. So this then becomes 11, and else we will just return none. So it's not one of the U4s, therefore we'll flag it later as one that needs to be accounted for as a full U8 and be flagged as a full U8 bit that's coming into our stream of data. So the other one that we're interested in is the space then, of course, space character. And again, we'll just copy and paste this across. So again, if it's no spaces, then it will be none. So this is going to be flipped. And this is going to be sum 11. So actually we are interested in that, and that's going to be part of our special character set. The other one is new line, which terminates, of course, a typical line of G code, and that is going to be sum 12. So we're getting there now. And G, so 13. Oops, put a comma there, and finish off the byte. And then we need byte of X, which is going to give us 14, and then anything else is going to be none. So those are all going to be treated still as U8s. What I like about the rest of this is that we can give it in the byte representation, actually give it in ASCII format, so I remember what the actual characters that have been encoded, and that's our forward lookup function. So we are taking our ASCII characters that we're interested in as part of our 15 most common, and then we're converting them into our effective U4s that we all merge together in a moment. We also want to then do const fn reverse lookup, which is going to do the same thing, but of course the other way around. So taking a byte, and again no spaces, and we still have to take, like I say, a full U8. We're going to retrieve an option, a full U8 character. In this case, we are going to again match on the byte, and this byte again is going to be really the entire forward lookup switched over. So we're going to just go, so if it's 1, if it's 0, oops, God, can't type today, here we go, sum 0, and we'll get the ASCII representation there now, and let's copy this all down. Oops, again. So we do 1, 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7. Copy those and do a load more. And now we will have some, oops, that's some 8, 9. We've got 10 is, if we go back up here, 10 is the period. 11, 12, 13, 14, 15, and 11 is, so that's our special one. So we need to also check if no spaces, else. Yeah, take back. So if it's no spaces, then it's going to be E. Otherwise, it's going to be space. 12 is new line. 13 is G. X is 14, and of course the 15th, which is actually the 16th for the special character, will be our none as well. So we're going to return none for any others. So that'll be in case we do get a full U8 we shouldn't have received, or the flag that it's a full width light continuing, and we'll return none there. So that's our oh no, we'll do there we go. Oops. Actually our 15th, so I was just checking. Of course we're going to return our flag, which is the 0, U80. So that's our flag to say, hey, this is the full width character coming through for this U4. We've got a forward lookup, we've got the reverse lookup, and now we can think about how we might pack some items. And to do this, we're going to create two functions here. That's it, the unpack and pack. So just find where I found these, and then I can take you through them. So we can do, let's do the pack. I'll just put it here. Pack. Debug. Let's do, yeah, we've got unpack. Right, let's do that one first. I found that one first. As I think the pack. How do I put that? Ah, of course, yes. I've put it in packable tab. I'll put it in the trait. Let's start with unpack first then. Let's say we've got a unpack, and this is going to accept a U8, and it's going to return two U8s, and it also needs to know whether we are dealing with any spaces or not in our algorithm. So this is going to return here at 2 U8s, a tuple of U8s. Oops, pop FN, and the byte. Okay, so the first bit we want to do is we can just create what our potential output is going to be, which is immutable. We're going to call it unpacked. it's going to be 2 U8s. And we can set those to 0, 0. It's actually not necessarily we don't need to necessarily do this because we can pack it later. So I'll just keep that there for now. So the first thing we want to do is the order of the unpacking. So we're going to start with we're going to get the most and then the least significant bits. That's it in the order in which we unpack two items. So we're going to then pack most and then least. So let the most equals byte, and we're going to bit shift this 4. So we're going to shift the most significant bits down to the least, and then it's going to clean out, and we're going to have nothing in the most significant bits anymore. They're going to be cleaned out, so we can then use this to then do our reverse lookup. So then our byte is going to be reverse lookup most. It's going to pass in those spaces, and I'm going to unwrap that because it will resolve to one of those options, because we know because of bit shifting we're going to be one of the U4 options available to us. Yeah, we just need to do there to stop those warnings there. So now we've got our byte that we've returned, and we can then do our unpacked. The first one is going to be byte. So our most significant bits U8 representation from the U4 is byte, and then we can do the least again. So the least is, we're going to take our original byte, we're going to shift it up 4 to clean out most significant. So we're going to take the least significant bits, move those over to the most significant bits, and then we're going to move them back down to 4. So back down to the least significant bits that we're going to check in our first lookup, and that's going to just clear out basically the most significant bits, so they're all zeros. Then we can do let byte equal reverse lookup least, no spaces again. Unwrap that because we know we've manipulated it in such a way that it's got to be one of the U4s, and then we can then add that to our tuple that then we return. So our unpack function again takes in that U8. We have then 2 U8s that we want to return. First of all, we look up what the most the byte that's represented by the most significant bit is, and we look at what the least the byte that is represented by the least significant bits in that original byte. We then put those together as a tuple and return that. So that's our unpack function, and reverse and the forward lookups. So now to actually use those in the library, rather than like always call these through using a U8, what I've ended up doing was add it to a trait. So I add it as a trait that we can then apply to any kind of variable, but any struct or type. But we're going to apply it to a U8 in our library, so then we can use that for any U8 that's being represented in the packing and unpacking code that we will build up in a minute. So to do that, we're going to create this pub trait called pack. This trait is going to support us packing. We'll take a self, and it's no spaces, and return an option of U8. So this trait is saying, like you say, if you implement this trait, you need to implement a pack function. If you it also then wants you to do we want to have a unpack function as well. So given a U8, what do you unpack into? So then it will need no spaces again. So factor those in. I need to do an option U8, U8. And then we could create this trait that we can then apply to or implement on any other type in our code. And what we're actually going to do is implement it on a U8. So we do implement pack for U8 and fmpack is actually, the packing function is actually effectively the forward lookup. So the pack, again, we just implement that above. It's going to return an option U8. And all this is going to do is then do our forward lookup with the byte. Oops. Self, sorry, this could be self, of course. And return us the option representation of our U4, whether it's a U4 or if it's none, to say then actually this U8 that you've got is a full width U8, therefore we need to flag it, add that flag, and then add it to our packed version of the G code. An unpack is going to be let's say it's going to be an option of U8. Oops, I need to put the cards around it. There we go. This is going to be an option tuple of U8s, and this is going to apply our unpack function unpack function that we're going to that we've just created, so unpack byte. So we then just put unpack pack self, no spaces, match types, found U8. So actually it's not an option because we know that a single U8 will unpack into two. We just don't know which two. So it's infallible there. So there we go. So that's our trait. And we've implemented pack for U8. So when we do, in a moment, create our packer function, we can then use that to unpack and pack. The other one that we created was pub trait pack tuple. So given a tuple of U8s, I want to have this function available to me to just call upon the two packing function to put those two U8s into a single U8. Okay, so I've called it pack tuple, and fn. It's going to be a pack function. It's going to take self and it wants to return. Here we're going to call it a result. So it's going to hopefully return us a U8 that's been packed, or it's going to return us an error. This is where first of the errors that we will create come from in our library. So so we're creating an enum called MeatPack error. And I've also implemented this error, so we can then propagate errors up through the tool chain, because this is going to be a low-level library. It's going to be depended on by many other higher-level applications or libraries themselves. So I used this error as a way of being able to propagate those on without them having to be, I believe you don't have to be dependent on, like, if I do any breaking changes, then it doesn't require necessarily you having to upgrade and have to do a breaking change release for higher level packages. So they can then just implement this error and pass those through. So just copy over that dependency. So this is this error version 2.02, that's 12, which is the one available. We've also got to put the default for options as false because it's a no stud environment, and it expects a standard library environment by default. So in our MeatPack error, bring up a reference. We have, we're going to say this derives debug, and it's also going to derive error from this error. And the first one we're going to have here is what's the error? It's going to say probably invalid byte. Check. Yeah, so we're going to implement invalid byte. So when you try and pack 2 bytes, of course, we want to make sure that they're 2 U4 representations and they don't have anything in the most significant bit of the U8. If it does, we'll return an error saying it's an invalid byte, and we will also return the 2 U8s that we were given, so people can debug further down the line. Actually, we're just going to return the byte that errored first. So do error, and we're going to say what's like invalid byte. So expected U4 received, and then we can pass it that variable. So that's the error that it should pop up now on line. If we ever reach it, it's going to say reached an invalid byte. We expected a U4 create as U4 maybe to say we know it's a U8, but maybe U4 representation in U8. Maybe you expected U4, U8 15. Received 0, because this will print out the decimal byte U8. So if we can then debug where we say, well, what value did we actually get? So pack tuple, MeatPack error. I'll close that off. So now we've got this trait called pack tuple. I want to implement that on implement pack tuple for 2 U8s. FN pack. Remember myself, so of course it takes reference to self. Copy that result over. And the first thing is we're going to try the pack the first. Well, first thing we're going to do our checks. So for the first byte, if it's greater than 15 U8, so it's not in our valid range of effectively U4s, then we'll return that error that we've just created. So return MeatPack error, MeatPack error, invalid byte, and we'll give it self.0 to propagate else. So okay, we will just put this as to do yet. We haven't finished it yet. We can do this again. So if self.1 is greater than 15 U8, then we will return error MeatPack error invalid bytes self.1. So we've checked our 2 bytes that are in our valid range, and we can do our packing function, which is then net packed will be equal to our self.0. So that's we're going to then bit shift that across. So bit shift that across 4. So that goes to the most significant bit of the byte. And then we can then do OK packed and effectively append self.1 there for that. So then that then fills in the least significant bit area, and because the you know, the most significant bit area there is all zeros. It's just going to take whatever self.0 was. So that's then packing the tuple. So this line is effectively the functionalities of pack and unpack bytes, which we'll be using throughout the packing side, where we read in the stream and pack those bytes. And we've also got the reverse lookup to unpack an unpacking function that will read in a series of bytes and unpack those. At the moment, we haven't got any tests, so I think what we want to do here now is to just introduce a couple of tests to show, let's say, if our logic is sound. Of course, we can do a CFG, and we can do test, mod test, use super. So let's import the functionality that we've just produced. And our first test, we shall test that G1, you know, that we had in the original command here. Let's use that G1 and say, okay, let's pack that and unpack it and see if we receive the G1 that we expect. So let's test fn test unpack, and what our first unpack test. So we're going to create a packed representation. So this is going to be right. We want the G and the 1. Okay, so we want our best to do this. Let's do dash if we do byte 1, we're going to shift that across. Nope, this is the byte representation of G. Shift that across. No, what minute? 13. We want 13, don't we? We want the byte representation, which the U4 representation, which is 13. Shift that across 4, and then we can then packed equals packed. What we can do, oops, going to give it a 1. Yep, just 1. Okay, and then so that should be our G and the 1 packed together. So then we can do let most least equal packed dot unpack. Here we go, and false because we're not doing any spaces. And as you can see, what that's just popped up there is that our unpack function, which we've attached effectively using the trait to our U8. We've implemented pack and unpack, and that's why we're able to call now, because we've got our packed, which is U8, represented by that, and then we can do assert equal most. We expect that to be the byte G, and we set equal here to least, and I'm going to put this as byte 1, the ASCII representation of 1, not the actual literal U8 of 1. Wait, 1. Oops. And that should be our first test. So if we go cargo test, oh, F right 5549. Okay, yep. So we've just got some warnings because we haven't used some of the functionality yet. That's okay. Go go back to our maybe it's this +1. No, should it be? I think that's the same representation as this. Why have I decided not to use the? That's fine. That's 13 should give us 3. 1 equals 1. As if I do the actual byte representation, what? Messing up with my bit manipulations here. Let's just do this for now. Oh, still not. Okay, so now my those bitnips were fine. Right. Nice. Bear with me. What's that? So that's that byte. Yeah, back. This should be G. Should be 1 right there. Bytes of forward lookup. He's 13. Stuff. My packing. Interesting. Right, let's see if I can print out. Right, extend create. Let's just import stud for now for a second. Use stud print line. See what we're getting. Okay, so what I've just done there is just printing, imported stud for our test cases using the external create command, using the print line to be able to then see a bit more detail of what's going on. So most is 71 and least is 50. Okay, so that seems to have returned, has done the conversions, but was it converted to? As card. U32. Can I just do from? Let's see. I'd accept that. Okay, so yeah, so I've got G and we've got 7. Why have we got 7? Did not meet 7. Right, so 1177. Look up for 7, so what I may have done, look up. Where the bug is that? Right. These. Oh. Right, reverse. No. Touch. Most released. Yep. Shift the byte up by 4. Move it back down 4. It's getting a. Let's do this in the test so we can see. We nip these what we're getting. We don't need the cars, we just need most and least here. Start up. Yeah, 13.1. Can't see it now. Right. So unpack. Have I done something in here? Unpack. Yeah, it takes unpack. So oh. That's all returned 1. Oh no, that's that. That would do best. Let's just try this, but it's not, shouldn't affect it at all. Nice. But we know that this fine. So that's 13.1. 1. 13 goes to G. 1. 7. Oh, sod. Right. Of course. Let's call that B. It's overshadowing. That's what you want. Apologies for that. There we go. Easy done. So, of course, we're returning a byte there. So we want that one to be be, so what was currently, we're of course shadowing byte here, of course it was taking that in there. So let's just clean that up. I think we're fine. Those, confident now. Yes, and we got it okay. Okay, so after myself there. So be careful of overshadowing your variables. We can now get one again, one that we expected. So I will keep it in byte form as it was originally. And now, so that's test unpack. And now we can do test packable. Take this as a byte of 0. So we don't expect this to work. No. Yes, we should be. Of course, it should work because it's 0. We should be able to pack this. So yeah, so it's a packable byte. So let pack equals packed. Oops. We'll call it packable. Sorry. Yeah. Before I start overshadowing my variables again. Packable.pack false because we're not dealing with no spaces at the moment. Unwrap. So error. We can't pack it. We should get past this. So we should say assert equal. We think packed should also equal just an OU8. Let's translate that. And whilst I'm here, I will do the test for an unpackable. So an unpackable one could be something like T, which is not in our special list. And packable, pack false. And what we want to say is we'll assert that packed is none of our special characters. Oops, we don't need to unwrap it there because we want to check if it's none. That's the two other tests I want to demonstrate today. Do those. There we go. So cargo test, and both of those are okay. So yeah, just a little minor issue there of just the shadowing there. So what we've got here is then the basics of the algorithm. It is those packing those bytes into a U8 and unpacking them as two U8s from a single U8, which is made up of two 4-bit representations of bytes. Let's see, I'm looking at time. So I think we can pause it there. I will then, in the next episode, we will continue on from this point where we can then look at taking these and creating the packer, which will then, loop through a series of bytes and pack those up, and then hopefully maybe also have the time to do the unpacker. We'll take those bytes and unpack them. I say all of this is on the actual real one. Is all in the Git repo and on crates.io. You can get to it there, and it's in docs.rs, and it's fully detailed, all commented up, so you can get ahead of the game if you want. I won't do all the commenting in here because it would just take too much time, but it's always good practice to do. So hopefully that was useful to show, like, actually this is all about, packing of bytes, and it's a bit of that bit manipulation, some nice lookups and forward lookups, and also a little bit of using of traits, where we can then apply it to generic U8 and a tuple of U8s, so that we get that functionality straight with our types as we go through our code. So that will become really useful. We create the packer and unpacker structs. So I'll enjoy the rest of your day, and I'll see you in the next one.